Rational expressions of the new unit we're looking at. First of all, you get a sense of a little bit what we're talking about if you understand the word rational. We talk about rational numbers, and they're better known as fractions. These are rational numbers when it looks like this. These are called rational numbers, or you know them better as fractions. Now, how we upgrade from learning about fractions to learning about rational functions, we don't look at things like this, we look at things like this, where we have a function over another function. Or we have something that looks like this over something that looks like this. These are called rational expressions because there's a function on the top and a function on the bottom of this type of arrangement. And so we're going to investigate everything we can about these kinds of guys. And we notice that there's like a function f of x on the top and a function g of x on the bottom. So do you see how these are like fractions? Fractions have a number on the top, a constant on the top and the bottom. These will have a function on the top and on the bottom. Now, one of the things that's important is about the denominator. In a fractions denominator, we never want a zero value. When you divide by zero, we get an error in a calculator, or we often call this undefined. And I'm running out of space to write that. Undefined. So in our world, we never want our denominator to ever equal zero either. We cannot allow that to happen. So here in this case, x can never equal 6. Because if it did, our situation here would actually turn out to be a zero number, and we can't allow that to happen. In a similar light over here, we wouldn't allow x to actually ever equal 0, because if you put in a 0 there, this all would become 0. And again, the idea is we never can divide by 0. This eventually represents things that cannot be in the domains. So in other words, these are values for which x can never be used. In this equation, in this function, you could never use 6 because of the problem it would create. And in this one, you could never use 0 because of the problem it would create. And these form what are called asymptotes of the function. So if your rational function was this one here, we would learn a couple important things. First of all, we can never allow that denominator. That denominator cannot ever equal 0. And so the number that we would be looking at is we could never allow that. X can never equal -10 because that would create a zeroing effect. In the same way, if I had this kind of guy here, I could never let this denominator equal 0. So in this case, I cannot let 2x minus 1 equal 0, and 2x equals 1. So x could never equal 1/2, because then what it would do is it would create an environment in here that would make 0 and then again creates a problem. This forms what we call asymptotes. Asymptotes. And these are lines that divide and break up the graph because we are not allowed to use certain values in that graph. And we'll look at that a little bit more. So here's a graph of a rational function. And we would want to look for the lines that would be the asymptotes, which in this case would be your horizontal line here at y equals 3. And it looks like, in this case, 1, 2, 3, 4, a horizontal line at x equals 4. These represent breaks in the graph and also known as asymptotes. And these basically represent locations that the graph never will get to. There's a reason for the design and make of this kind of function, and it is restricted that it will never use those values. So for instance, this graph might look something like this if I was just to create one that's like this. This could potentially be this graph, and we'll explain more about this in a minute. But the idea is that because of this, we cannot ever equal this, this vertical line here. We would be restricted in this way. And in a minute we'll learn that something to do with these values here is what restricts us going this way. And so at this stage, though, we learn that x cannot equal 4, and that's why this line exists. And so it breaks one part of the graph and the other part of the graph into two pieces. So these are two examples of the more basic variety of this, and this is mostly what we're going to study. This rational function is in the format of ax plus b over cx plus d. Now what we mean by that is that, for instance, the 3 would be like the a, the -1 would be like the b, the 1 here would be like our c, and the -2 would be like our d value. So if we were trying to find the vertical asymptote, which means what values can we not use here, x minus 2 cannot equal 0. And when you solve that, you get x cannot equal 2. So that becomes our vertical asymptote through x equals 2. The other thing that we learn is that the horizontal asymptote is basically the ratio of the a to the c. Now in our case, the a value was a 3, and what I'm talking about is right here. There's our a value of 3, over our c value, which is here, which is a 1. And so that would mean that this line would exist here, and it's y equals 3. So our graph would have to exist bounded by that red and that blue line. And to graph this more correctly, you would want to plot some points. But basically the idea is you're going to get a hyperbola-like shape bounded by those particular lines. So let's do the same thing for this one over here. Let me just clean us a little space and we'll do this one more time. So likewise, our a is here, which in this case we don't have an a value. Our b value, the constant, is the 5. Notice there's no a value. There's nothing times x in that top group. Our c value is here at 1, and our d value is here at 4. So again, if we were to solve for when that denominator, when that x plus 4 cannot equal 0, we would find out it would be at -4. So again, x cannot equal this -4 line. The second component is the horizontal one, which is a over c. Now in our case, our a is a 0. Why do I say that? Because notice up here, there is no a part. There is nothing multiplying by x. So it's 0 over this value, which is 1, which is just 0. It's okay to divide into 0. You get 0 times. You can just not divide by 0. So this line would actually look like this one. And again, we would create, with a little more exactness, our hyperbola-like shape to form our graph. This is the beginnings of rational functions.